So today, as promised before, we are going to start chapter number 13, which is about gears, and it is basically a more general chapter about types of gears, and we're gonna go over the outline together just to show you and to size your expectation. So we are going to talk about types of gears. Finally, we always talk about them, but we not in details. Then we'll talk about the nomenclature. If you are not familiar with the word, it's like a vocabulary sort of thing. Then we'll talk about the conjugate action and involute properties. And these two parts are very fundamental for gearing, or gear law, if you want to call it, and we'll see why. Then we'll talk about some fundamentals, contact ratio, interference. This part, which is 13.8, is dedicated for machining. We have straight bevel gear, helical gear, and worm gear, and then we'll do, of course, most importantly, the force analysis for them. This is actually very important. These gears, when they engage together in action, they generate forces, and these forces get transformed or transferred to the shaft, and then from the shaft to the bearings, and so on. So starting with the types of gears, the first one is the spur gear. This is the most well-known gear type ever, because I am pretty sure you have seen this a lot. You have a toy with some wheels or some moving parts, you will probably see a spur gear. So spur gears, what are their characteristics? Well, the first characteristic one, the first and most fundamental one, is that their teeth are cut parallel to the shaft, parallel to the shaft axis. Which means, if you look here, for example, you have this shaft, and this is one gear. There is another shaft. So the two shafts are parallel, and we have two gears. As you see, this is the first one, and this is the second one. So what usually we do is this. As you know, I mean, just as a general overview, I know you know this very well, is that here you have all the teeth for gear number one, and then the teeth for gear number two. Now, what happens over here in such an arrangement, whenever we have a small gear, this one we call it pinion, okay? The other one we call it just gear, the bigger one. Now, apparently, it's very clear that when the red gear over here start from there and then rotate one single revolution, the other gear would probably rotate multiple ones. So let's say 3 revolutions. So what you are doing indeed is you are like, this is a mechanical multiplication. Yeah, like just math, when you multiply two numbers, then this is a mathematical multiplication. So, so what happens if you do the reverse? If you do the reverse, then as we all know, it will take you multiple revolution of this guy to make one revolution of this guy, which means you are actually dividing. Yeah. So this gear ratio thing is always probably in need. We usually transmit the power through rotation, and with that, we play with this ratio. We either increase it or decrease it. Good. Now, the second type of gears is called the helical gear. We have talked about helical gears. We mentioned them several times. They are also arranged in a way with their axes. The shafts are parallel, so it's not different from spur gear. But the difference here is that their teething system has this inclination, okay? And why is that? Well, it turns out that by doing so, the spur gear, helical gears become less noisy. The reason why is because the spur gear, ya shabab, they come like this, and then the tooth from one touches the other, and then they separate, and then the other one, and then the other one. While in helical gear, if you look only at the teeth, the engagement of the teeth become gradual. And that gradual engagement makes it less noisy. Of course, with that, you will generate a thrust load. And we know now how to deal with it. It's an extra force. It doesn't happen with a spur gear, but it's all right. We can survive now. We know how to deal with that. So I am showing you here an example for a gearbox for a car. Now, with all reservation that maybe I'm not going to say many, I'm going to say students in general might think that the purpose of mechanical engineering is automobile, cars, which is totally not true. Ya shabab, you should be proud that mechanical engineers made a lot of machines. A lot. I mean, car is just a peanut compared to what we made. So, but cars are very important. Why? I mean, look around you. We have probably billion something car in the planet. You probably have a car. If you don't own your own car, you are driving one. It's not like airplane. Have you ever fly an airplane, ya shabab? I don't think, and maybe you will not. So that's another machine. And but don't get it wrong. Cars are very important, and bringing an example of cars here is just because they are much closer to us. Okay, it's not to tell you, oh, this course is for designing cars. That's the matter. So this is a gearbox, and as you see, the whole gearbox is full of helical gear. Not a surprise. Helical gear, all of them. And it is a very fundamental piece of, the car. And so the next one is also the bevel gear. So that's the third one. So helical gear will produce a thrust, are less noisy, and bevel gears have a totally different characteristic, which is the fact that if you look, again, this is the differential of a car. So we're still with cars. The car engine is somewhere here, which will produce rotation through combustion. And then the shaft over here, the main shaft, will rotate. Now the challenge is you want that rotation to go along this. That's an intersecting shaft. They are not parallel. So because the wheels are here, and that's how you drive the car. So how do you do that? You do it with bevel gears. So bevel gears are used whenever there are intersecting shafts. Okay. Now, again, bevel gears are very important because you know that this is the differential, this guy, and the differential is very important piece in the car.
Doctor.
And if you look, by the way, just to show you something interesting, Faris, do you want to say something?
Yes, the only condition here is between the two axes is to be intersecting, or they need also to be perpendicular to each other.
Well, I think they, most of the time, as far as I know, they are perpendicular, okay? Like in this way. But I am not sure if this exists. Honestly, this is more like a practical information than a scientific one. Depending on the way how you cut the teeth, maybe if this is cut with different angle, then you can have them coming like this. This is one shaft. Sorry, the gear has to be like this, and then maybe you have another gear like that, and in that sense, the two shafts are not actually perpendicular, but they are intersecting. Does this exist? I don't know, honestly. I need to check it maybe next time. So just for a bonus, you see here, we have, this is a real differential, ya shabab. This is where we have a roller taper bearing. Very interesting, right? Of course, in the other section, there was a student who said that it is wrong to change the oil for this guy. And because I told them I changed the oil for the differential. So I just thought I would tell you that I changed the oil for this guy, and probably I am wrong based on the culture. So, so what happened over here is the fourth type, ya shabab, is the worm gear. The worm gear is also very fundamental part of the car, because actually, if I'm not mistaken, if this is still the way it goes, the steering wheel, when you steer your car, that long shaft will end up joining another shaft in this way, and that's how you steer. But in general, this is called the worm, which is like a screw. If you think about it, this is just like a screw. And this one is called the worm gear. Okay? So, or sometimes they call it the worm wheel sometimes. And there is a convention for the rotation, how this would rotate clockwise, and this one rotating in a clockwise or counterclockwise. We can talk about it later. Now, what do we want to get into is the nomenclature. Now, what you would think is that gears, you might underestimate them, and you think that these things are available in the market, so why bother? Just buy them and that's it. You will be surprised how much math is there onto gears. I mean, it is very well established. I have to tell you this. As far as I know, gearing is very well established, which means, I mean, you don't see, ya shabab, often these guys failing. Unless you are a drifter, you drift, this is against the law, or maybe because you did something wrong, or maybe we didn't change the oil. I'm trying to prove myself right. No, I'm not kidding. I'm just telling you, whatever, I mean, these guys, you don't change them in the car often. You change the shoe for the brakes, they are really reliable. You understand that? If you do the right thing. I mean, these can get overloaded if you put a load on the car, which is way more. You can overload these things, and you can probably damage the gearing inside, and that's it. We know that gear, box, engine, three biggest element in the car, and they are very costly usually. There's a lot of, you know, mechanics is in there. But in general, this is very well studied. I can show you. I mean, you will understand probably by end of this lecture and then probably part of next lecture that this profile has way, this profile has way more into it than what you think. Way more. Okay? There is a lot of math done on this guy. And why is this? We'll come to it soon. I'm not trying to scare you off. We're not going to do a lot of math. I'm trying to tell you that don't underestimate things just because they exist and somebody did them. And you say, oh, this is cheap. This is not important. This is easy. There is a lot. It is easy because somebody did the hard work. Yes. So be careful. Give it its own weight. Now, we will start with the terminology. So as we all know, gear, you would imagine that it is a disc, and then in the disc you come and then you machine those teeth, right? And when you machine these teeth, what happened? You will have them cut in a specific way. The first thing that we want to establish between us is the term pitch circle. This is the first one and the most important one. Why? The pitch circle is a theoretical circle. It's actually, look at it, it's over there. That's the pitch circle. Somebody might ask why it is here. Is it in the middle? Huh? Is it not? Why here? Why there in that position? Well, that circle is actually representing the whole action. So when I draw a gear like this, that's a gear, and let's say I have a pinion like that. What did I draw, ya shabab? What did I draw? Two circles. These circles are actually the pitch circles. And by the way, intentionally, we do it without feeling, without knowing, but we are actually having this point, and this point is along the tangent when these two circles touch. Yeah. So this circle has a diameter, because if it is a circle, then it has a diameter. The diameter is called the pitch diameter, which is very important. Whenever they tell you this is a pitch diameter, it is not in the root over here. It is not on the top. It is somewhere this imaginary theoretical circle. Understood, ya shabab?
Doctor?
Yes.
Could you please repeat where is it located, the pitch circle?
We will talk about it. Don't worry. Now, I want you to know that this pitch circle is here. How much is it? What is it? What is its size? That's something will come. For now, you need to know that there is a circle in here, which is called the pitch circle. That circle is very special. It has an exact location, exact dimension, which we will talk about. Okay. Now, the pinion is the smaller gear. We talked about it. So this is among the terminologies. Then we now go to the circular pitch. Now, the circular pitch is more or less, ya shabab, just to remind you with chapter 8. Chapter 8 for screws. When we draw the thread for the screws, what did we say? Say that if you go from this point, which is the peak, and then to the next adjacent peak, this is called the pitch. This is more or less the same. So what I'm going to do, I will come to the side of the gear, and then of this tooth, I will look on the adjacent side of the next tooth, which is this one, and then along the pitch circle, I am going to mark the intersecting point and then I will measure this distance. This is called the circular pitch. It is circular because it is around, and it is a pitch. It repeats, just like the teeth. You understand? Now, so the circular pitch is the sum of the tooth thickness, which is this, plus the width of space. So indeed, that distance is decomposed into the tooth thickness plus the width of the space. Okay? There is another term which is called the modulus, and it is, abbreviated as M, and it is the ratio of the pitch diameter to the number of teeth. How many teeth are there? You count them, and then you go to the pitch diameter. You remember? The pitch diameter is you look at the pitch circle and you measure its diameter. So you take that diameter, you divide it by the number of teeth, and then you get the module. Now, I am pretty sure you are now saturated probably and even overwhelmed, and you cannot accept more names. But don't worry about it. They will look difficult, too much, confusing, but with time, you will get familiar with them. Yes,
Sure.
Faris. Yes.
Why didn't we define the what is it called? Pitch. Can you go back to the previous slide?
The pitch, circular
pitch. Yes.
Why?
Isn't it defined from the center of the teeth to the next center? Why do we measure it from the face and we state in the definition we add the space
it's supposed to be the same. صح ولا لا?
صح.
Could be, but I think it is easier for measurement. I mean, if you bring the vernier or whatever possible tools there, you can easily stick it here to there. But finding the middle is difficult, and I think it's just a convention.
Okay, clear.
Okay. So
Doctor?
now we go. Yes.
Is it measured from anywhere along the surface or only along the pitch circle?
No, the intersection here of the circular pitch to the. I think these numbers have become very important when you form your gear. So but when you buy the gear, you will know these values, but they are very important when you want to design it. Okay, I know that we say it most of the time. You are gonna buy the gear, but remember, ya shabab, who is making those gears? Do they grow from trees? No, they're human beings making them. Now, the fact that you may not work in a factory that makes gears doesn't mean that you don't know how they work. You are a mechanical engineer. At the end of the day, when we speak to you about the conjugate action and no, you will understand that the only person who can make this thing right is a mechanical engineer. I mean, nobody can just come and jump and make a gear. It's more than what you think. You will see it in a minute. Now, so the diametral pitch is the ratio of the number of teeth to the pitch diameter, which is the reciprocal of the modulus. So we said that the modulus is the pitch diameter. Was it? Yeah, the diameter. Let me see. Which is D over N. We will see that the diametral pitch is equal to N over D, the reciprocal of it. So we have also, if we cross this line and say that this is the pitch circle, then what is above it? From the pitch circle all the way to the tip of the gear. This is called the addendum. I know it might be a very weird term, but we should wait for the next one then, because the next one, which is the distance from the pitch circle all the way to the root, the end of this cut over here, the root, this is called the dedundum. So this is A, edundum. This is called B, which is the dedundum. Okay. Now, what you should know is that the whole depth from, which is the whole depth from here all the way to the bottom over there, is the sum, which is called the whole depth. It's Ht, and it is the sum of the addendum plus the dedundum. All right. Now there is a clearance circle, which is this circle. This circle is parallel to the pitch circle. So if this is the pitch circle, then there is a circle which is below it, and it is parallel to it. Okay, and that circle, okay, is basically representing the gap, which is the clearance C. This clearance is between the clearance circle and the root. Why is that clearance there? Because you will see later, we'll show you that if this is one tooth and the other tooth is coming here, the other tooth will come and then it will not go all the way. There will be a gap over there. That gap is called the clearance. Okay. We move on. There is something, the last term, which is called the backlash. The backlash is another clearance, but it is over here. Look at it. That gap over there. What is this gap? Well, this is the pitch circle for the top gear. This is the pitch circle for the bottom one. Again, as we said before, they are going to be touching. This is where the tangent action is happening, the tangency, okay? And of course, we will show you later that that tangent, if we draw perpendicular to it and so on, and then we connect the center of the gear, we can find the pressure angle, which you heard about it a long time ago, but you don't know how it came exactly. So this is called the backlash, okay? The backlash is over there, which is a gap. So while the gears are touching here, they are not touching in the other side, okay? Now, so if we want to write this represented quickly and in a mathematical way, the diametral pitch is equal to the number of teeth divided by the pitch circle or the pitch diameter, and the module is basically the diameter over the number of teeth, so it's the reciprocal. We have also the circular pitch over here, which is this much, right? That's the circular pitch over there, that much. It is by D over N, which is by M. And we can also show that the multiplication of the pitch circle or circular pitch multiplied by the diametral pitch will give you pi as a constant, right? Now, we will come back to these more and more. This is just an introduction about what's going on. So now we split things into, we gave them name and terminologies. Now, the idea of the gearing, ya shabab, is that it lies around one particular commitment, if I want to call it. Commitment means the gear must deliver this. What is that commitment? What is that thing that the gear will deliver? Okay? It is constant angular velocity ratio. You see that? So what is our target? Our target is that the gear, while they are mating together, okay, they will always deliver or operate under a constant angular velocity ratio. This is not going to sink in your head easily. I may sound repetitive and boring, but I have to sink it in a little bit by little bit. Now, how is that? If they deliver this constant angular velocity ratio, then that action of delivering constant angular velocity ratio is called the conjugate action. Now listen to me carefully. In theory, here it says, at least it is possible arbitrarily to select any profile for one tooth. Just any profile. The tooth is like this, whatever. All right? That will give a conjugate action. So you can just randomly play. You may ask a question right now. Which is this conjugate action? Why is it so difficult? Just put two gears, they touch and then they go, they touch and then they go. Why are we making it difficult? Why? To fail in the exam, right? So one of the solutions is the involute or involute profile. So what is an involute profile? It's basically a description of this curving or curvature, which is going to mate with another gear. And I want to tell you this up front. When the two teeth come in contact with each other, they will touch. That's not surprising, right? That's how the drive happens. But they are not gonna just say, okay, let me, and then touch the gear and then fly away. No, they will come like this, engaged, touch, and then leave. And then another one will come, touch, and then leave. And then another one. Now, what do we want to do is that if you think about it, while they are touching, the point of contact is moving. It's like they are not sitting on the same point because one of them is moving this way, the other one is moving this way. So that point of touch is moving. And when the point of touch is moving, in a simple way, I'm trying to explain it in a simple way, this is what you might expect. For example, we all know from dynamics that if I have a rigid body, which is pinned to the middle, and it's a circle, so it has a radius r, and it is rotating with an omega, okay, then the velocity v equals to omega r. My focus is on the omega because I want omega equals to v over r, and my eye is this. I am trying to say, okay, what if there is a pinion over here, okay? And this one, let's call it gear, and then the velocity v gear. So over there, this is gear, and then the ending gear. Now, what happened for the pinion? I will have v for the pinion equals to omega of the pinion, r for the pinion. And similarly, I will have the omega for the pinion equals to vb divided by r. Yeah. So what do we want is to, while these two circles are in action, we want the ratio of the angular velocity, the ratio to remain constant. So one of the ways, as I said, is the involute, I mean. So what is the story over here? Let me try to explain it. This is like a cam, you know? Cam is a very common device. It's available I mean, it is also part of the car. A cam is the element that rotates in the engine, and when it rotates, it touch the valve open, the gas get inside, and then when it moves, the valve closed. So it is all, it's like in here, if you think about it, in here, we have this one, consider this mechanism. This is now pinned over here, right? So if you were to imagine that this arm over here is also pinned over there. So this blue arm will rotate. No doubt about it. Does anybody has any doubt? No, it will just rotate. Forgive me, that's a very ugly, that's like a wood fire, you know, like in camping.
Yep.
So yes. And the red guy will also rotate. So the red guy is here, and then after you push it, it will go like there, right? And then you push it further, it go like there, and so on. But when the blue one is here, this one will come back to its initial 0. And then the blue one will move, and then, oh, it touch it, and then it push it. And then it goes away. Then this one will come back, and then it touch it, come again, and again, and again. Now, we are not interested on what happened after the blue one become not connected to the red one, or before. We are just interested in the moment when these guys come and touch each other. Understood? Now, what will happen then is this, which is the first one, okay? The first one is that when they touch, they will come in contact at point C. Now, point C is the point of contact. And we can easily, from a geometrical point of view, draw a tangent, right? And when we draw the tangent, we know that the perpendicular line to the tangent is actually the line where the two forces are going to act in opposite direction, but with the same magnitude. Is that correct? Is it difficult?
No.
It's just simple now. Now look what happened. For that reason, since the forces are acting on the yellow line, we will call this one the action, or the line of action. Line of action. Now, look here. I want to tell you, look what happened. If you construct, okay, a point, right, a line from the center O to the center O of the other cam, you know, like two mechanisms, two arms, something, then you will get a there. What happened? That red line, which is always fixed, that red line is always fixed. This will never change. The yellow line might change depending on the tangent. What if the tangent is here? The yellow line is perpendicular to that tangent. It will go like that. Am I right? So the yellow line might move. Remember, that contact C will move a little bit. They will stay in contact for a little bit, and then they will leave. That little bit is what we are trying to explain over here. Now, what if, let me clean this up. What if, clean this, and then make sure I draw, yalla ya shabab, remember this is the line of action, and this one is our red line, which is connecting the two centers. This is the point of contact. This is the intersection point between the centers and the line of action. This point is very important. Why? You don't need to know now. I'm telling you it is important. Just keep it in your head. And for that reason, we are going to extend a radius from the center over here all the way to the point B, and we will draw, and then we will draw a circle representing this line, okay, this whole curve, which is represented by the radius from the center of the arm B until point B. Now, what if I do the same with the other circle? I go and I draw a line from the center of it all the way to point B, and then mark this as a radius. And when I mark it as a radius, I'm gonna revolve it. And when I revolve it, I will get this circle. Yeah? Now, why I'm doing this? Why? Well, this is what is coming next. Now, it turns out, ya shabab, that angular velocity ratio between the two arms is inversely proportional to their radii to point B. So what happened? Look, this radii, okay, will construct the relation between the angular velocity ratio. Now, be careful. I said the angular velocity ratio, which I want to make it constant. So how can I make it constant? If that ratio is inversely doesn't mean anything, right? Is it proportionally or inversely proportional? That's a proportionality. What matters is this, is that ratio that I want to make constant is related to the radii, which is RA and RB. How can I make the two radii fixed? Because if I make them fixed, they will not change, and the ratio of the angular velocity will never change. Now, somebody might say, can we make them fixed? We just said a minute ago that one possibility of contact is here. I'm gonna make it yellow, and the tangent was here, and the line of action for it was here. So what happened if the contact become a little bit below? Well, the tangent might change just a little angle. And when the tangent change, this one will change. And when it change, look, the line of action now will intersect this red line at a different point. So point B will change. We reached a dead end then, right? But this is the question now. If you did this profile with this one in a very precise way, listen, very precise way, you can actually do the magic. What is the magic? Every time the point of contact change, let's say there are 3 points of contact, and then the separation happens, you will have a different tangent. But when you draw the line of action, it will always intersect with same point B. So you make the profile such that as the tangent change, its perpendicular line will always pass through point B. If that happens, what is the result? Point B will become fixed. And if point B become fixed, then RA and RB become fixed. And if they are fixed, then the angular velocity ratio the question now, how can you do that? How? How can you do this touching and movement of the point such that the tangent and its perpendicular line will always pass through the same point? You just need to draw that profile in the right way, and that can happen. Interestingly, ya shabab, it's possible. That's why we have gears everywhere. Like almost all of the gears, most of the gears, universally, are designed this way. When just imagine that this whole thing here, we did it, is between a cam, like a link and a little, you know, geometry, curved geometry. But later, ya shabab, what are we gonna do? We are gonna see that this is exactly what I explained to you, just in steps. So that's what is known as the involute or involute properties. So next class, I'm gonna show you how this involute is constructed, and after which we are literally gonna have these teeth come touch each other. Like, look, this is one teeth and touch each other, and the point of contact will move. But as the point of contact moves, their tangent will make the line of action always pass through the same point. Fantastic. And with that, we are truly guaranteeing that the angular velocity ratio is constant. I hope you get it, ya shabab. Next class, I promise you, I'm gonna have some nice image. Some of them are GIF, you know, GIF, and you will see things moving in action, and hopefully it will make you feel it the right way. Okay, this is it, ya shabab. Today, for this class, I wish you a happy week.